Well, now we're going to take a look here at example number 5 and actually get around to something that we've been dying to do almost since the start of chapter 3. A long time ago, I introduced to you the power rule, and we introduced it by looking at identifying some patterns in derivatives of x squared and x to the third and x to the fourth. And at that time, I had asked you to just believe me that our good old power rule, that is the derivative of x to the power of n, actually would just always equal n times x to the power of n minus 1. And I said, just believe me right now. Well, now that we finally understand the ideas of derivatives of logarithmic functions and logarithmic differentiation, we can actually go through and finally prove the power rule. And so let's go ahead and do that here. This will actually allow us now to have shown every single power or every single derivative rule proof, except of course for that chain rule proof, which I said was going to be a little bit complicated. So let's go ahead and take a look here at how we would do this. I'm going to go ahead and start by saying, let's suppose that y is equal to x to the n. So this is the thing I want to take the derivative of. And we'll say where n is some constant. Let me write that. So n is just some constant. And we'll say that x only takes on values which make y a real number. So all I'm really saying here is that I have to be a little bit careful. If n is something like a 1/2, then technically this is a square root function, right? And I would have to make sure that x would then, in that case, not actually end up being a negative number. If n, however, though, was something like a power of 2, then I don't really have to care what the value of x is. I could plug in anything. So the options for x do really depend, or they vary, based on what the value of n is. And so I'm just saying I'm only going to consider values of x that are going to actually make y spit out a nice real number. So with this kind of defined, we can go ahead and note a couple quick things. So I'll say, we note that y is equal to x to the n, and this right here actually implies the following for us. It would definitely imply that if I wanted to do the absolute value of both sides, these things would still be equal. And in fact, I could go one step further by saying that I could guarantee that the right side was definitely going to be positive if I just absolute valued x and then applied the power after. Like applying a power to a positive number can never make it negative. Now, the reason that I'm going to do this is because I'm going to be trying to use logarithmic differentiation. And that's going to require that I take logarithms of both sides of my equation. But I can't take logarithms of both sides of the equation unless I can guarantee that those inputs are going to actually end up being non-negative values. Okay? So I'm going to go ahead here and take a look at the following. So now that I have this, I can go ahead and take this one step further. I can now do the natural log of the absolute value of y, and that would be equal to the natural log of the absolute value of x raised to the power of n. And of course, by using my properties of logarithmic functions, I can say that my natural log absolute value of y would then be equal to n times the natural log of the absolute value of x. So now I can jump to my derivative. Say we then compute that if I took the derivative of both sides, so I took the derivative of the natural log of the absolute value of y, that should be equal to the derivative of n times the natural log of the absolute value of x. Now again, I'm doing this derivative implicitly. So on the other side here, remember that I'm going to get 1 over the value of y. Right? Remember that the derivative of the natural log of the absolute value of y, we said it was actually going to be just 1 over y. Right? And we did that actually back here in our example of part C on example number 2. Derivative of the natural log of the absolute value just ended up being 1 over that input anyways. So that's all I'm making use of here. So I'm just going to be able to state that this is going to be 1 over y dy dx. And on the other side, notice that n can stay as a constant, and I'll just get 1 over x here. Now, of course, if I get dy dx all by itself, I'll have to multiply y over to the other side here. But of course, if I was to go ahead and replace y with what y is equal to, I know that y is equal to x to the power of n. And so I end up with this. But notice here that I have now x to the power of n, and I have a division here by x to the first power. And so if I was to go ahead and write this in a simplified form, you'll see that I would end up with n times x to the n over x to the 1, which of course is equal to n times x to the n minus 1. And there it is. That is actually the derivative rule of the power rule. But now we've been able to actually show that that rule works. We have a nice proof for it. So again, what this means is that we've actually been able to take a look at every single derivative rule on this sheet, except of course for the chain rule. And we've been able to show exactly where each one of these individual rules comes from and why it works. And that is so important. That's doing mathematics, understanding what we're doing and why it works and where it comes from. So hopefully that's actually definitely kind of a really interesting look into how and why these things are true, and something that if you've taken calculus before, maybe you were never actually able to see. So in the next video, we're just going to end by talking about a final interesting fact that can sometimes be important in Calculus 1 and Calculus 2.